Hello, Matthews Gatos here. In this lesson, we're going to look at slant asymptotes. So let's talk about what a slant asymptote is. It is defined as an oblique line, and an oblique line is just a line, y equals mx plus b, that is not horizontal and not vertical. So in other words, an oblique line is a line in which the slope is not zero and the slope is not undefined. So a slant asymptote, oblique line, in which the graph approaches at the ends of the graph. So as x gets really, really big positive or really, really big negative, it's where the ends of the graph are going. So we looked at horizontal asymptotes, and horizontal asymptotes were where the degree of the numerator and denominator were the same. Slant asymptotes will happen when the degree of the numerator is one more than the degree of the denominator. And if you remember when we did in 30-1, if the degree of the numerator was bigger than the degree of the denominator, there was no horizontal asymptote. Now you're going to see there could be a slant asymptote if the difference is 1. So if a function has a slant asymptote, it will not have a horizontal asymptote. Here's the formal definition to prove whether a line is a slant asymptote or not. If we look at the limit as x approaches positive and negative infinity, that just means the ends of the graph. And we look at the difference between the function and the slant asymptote. This is just the slant asymptote. That will approach 0, which just means that the ends of the graph are approaching this slant asymptote. So the distance between them is getting smaller and smaller, and it is approaching 0. So let's look at an example here. I have this rational function f of x, and I want to prove that x plus 1 is the slant asymptote. So I have a little picture of what the graph looks like. So the function there is in blue, and you can see the slant asymptote is in red. So what we want to prove is that this slant asymptote is in fact x plus 1. Well, we'll do that with our limit definition. So we're going to look at the limit as x approaches positive and negative infinity of the function x squared plus x plus 1 over x, take away the slant asymptote. So take away the slant asymptote, which is x plus 1. So to do this, I'm going to do it with a common denominator. So I have x squared plus x plus 1 all over x. And then this is all going to be over x as well, as that is the common denominator. So x plus 1 will be multiplied by x. Okay, so let's tidy this up, and then we'll separate it into our two limits. So I have x squared plus x plus 1, and then I'm going to take away x times x and take away x times 1 all over x. Okay, and you can see there's a whole bunch of things that cancel. X squared take away x squared is gone. X take away x is gone. I'm just left with 1 over x. So I'm going to look at the limit as x approaches positive and negative infinity of 1 over x. So let's separate these out. So the limit as x approaches positive infinity of 1 over x, and the limit as x approaches negative infinity of 1 over x. So remember before, when we were talking about limits, we said whenever the denominator has a higher power than the numerator, the limit is 0. So if I have 1 over a really big positive number, that's going to approach 0. Similarly, if I have 1 over a really big negative number, that will also approach 0. So since this is true, I can therefore say that y equals to x plus 1 is the slant asymptote. So that's how I verify it. The next two examples we're going to do, we're going to look at how do we find the slant asymptote, and how do we know what the end behavior of this graph is going to look like. So the method that we're going to do is very similar to the horizontal method that we used. We are going to use long division to write our rational function as a division statement, and the division statement will be the rational function, this is f of x, is just going to equal to the quotient plus the remainder out of the divisor. The reason we're going to do that is because the quotient is going to be the slant asymptote. So that is the slant asymptote. The remainder is going to help us determine the behavior, the end behavior of the graph. So if we look at the limit as x approaches positive and negative infinity of the remainder, if that limit is negative, then the curve is below the slant asymptote. If that limit is positive, then the curve is above. So let's try this first example here. So first of all, I just want to check to see if it does in fact have a slant asymptote. So the degree of the numerator is 2, the degree of the denominator is 1. The difference between those is 1, so I know that I'm going to have a slant asymptote. To figure it out, let's use long division. So negative x squared divided by x, negative x, and now I just multiply. Negative x times x is negative x squared, negative x times negative 1 is positive x, and then I just subtract. So negative x squared take away x squared, negative x squared is 0, x take away x is 0, and I bring the 1 down. So that means that my rational function written as a division statement, negative x squared plus x plus 1 all over x minus 1, is the same as my quotient plus my remainder out of my divisor. So this will be the slant asymptote. This will be the remainder and the end behavior. Okay, so I want to graph y equals to negative x. So that is the line like right there, y equal to negative x. And now I want to determine the end behavior. So what happens at the ends of the graph? Will the curve be above or below? So let's do the right end first. So I'll look at the limit as x approaches positive infinity of the remainder, which is 1 over x minus 1. So if I put in a really big positive number, huge positive number, and I take away 1, it's still just a positive number. And 1 over a positive number will be positive. Okay, so that tells me that as I approach positive infinity at my right end, it will be above. So the right end of the graph right here, the curve will be above the slant asymptote. Let's look at the left end. So I'm going to look at the limit as x approaches negative infinity of 1 over x minus 1. So if I have 1 over a really, really big negative number, take away 1. Well, take away 1 isn't going to change the fact that it's a really big negative number. So 1 over a big negative number is just negative. So that tells me that my left end, since it's negative, will be below. So the curve will be below the asymptote. So if I look over here, this end will be below. We're going to work later to figure out what's happening in the middle of this graph, but for right now, I do know I have a slant asymptote, and I do know what the end behavior of that graph will look like. So let's look at on the calculator just to see if that's reasonable. So on the calculator, I'm checking, was the right end of the curve above? And you can see in blue, it is in fact above the red, which is a slant asymptote. Was the left end of the curve below? Again, in blue, you can see here that it is in fact below. So let's try one more. Okay, so for this graph here, I want to look at the degree of the numerator is 3. The degree of the denominator is 2, and the difference between those is 1, so I do have a slant asymptote. Now, to find that slant asymptote, let's use long division. So I'm going to do x squared plus 1 into 2x cubed minus 3x squared plus x minus 3. Okay, so 2x cubed divided by x squared is just x. So 2x times x squared, 2x cubed. 2x times 1 is 2x. So I'll just line the x's up like that. So subtracting. 2x cubed take away 2x cubed is nothing. Negative 3x squared take away nothing is negative 3x squared. And then x take away 2x is negative x, and I'll bring the negative 3 down. Okay, so negative 3x squared divided by x squared is negative 3. And again, multiply it through. So negative 3 times x squared. Negative 3 times 1 is negative 3. And then subtract. So negative 3x squared take away negative 3x squared is gone. Negative x take away nothing, negative x. Negative 3 take away negative 3 is 0. So my polynomial written as a division statement would look like this. 2x cubed minus 3x squared plus x minus 3 all over x squared plus 1. Oops, there we go. X squared plus 1 is equal to the quotient 2x minus 3 minus, because it's negative, the remainder over the divisor. Okay, so looking at this, I can see here, this is my slant asymptote. So 2x minus 3 is my slant asymptote, and this will be my end behavior. Okay, so 2x minus 3, let's do a little sketch of that. So it has a y-intercept at -2 and a slope of 2, so up 2 and over 1, and I will just connect those dots together. So like that, and then in the other direction as well, just as a little rough sketch here. Okay, so now I have my slant asymptote. I want to figure out the end behavior of my graph. Okay, so looking at the limit as x approaches positive and negative infinity. So let's look at the limit as x approaches positive infinity of the remainder, which is negative x over x squared plus 1. Okay, so again, we're looking at a big number, a big positive number. So if I put in a big positive number, negative times a big positive number, all over a big positive number squared, plus 1 isn't going to really change a big number that's squared and even bigger. So if I have a negative big number divided by a big number squared, that's just going to equal to a negative value. So that means that the right end, as I approach positive infinity, will be below, the curve will be below the slant asymptote. So over here, I know the ends of my graph will be below. Okay, let's do the same thing on the other side for negative infinity. So the limit as x approaches negative infinity of negative x over x squared plus 1. So I'm going to have negative, a big negative, all over a big negative number squared. Plus 1 isn't going to change anything. So a negative, big negative, two negatives is going to make a positive, over a big negative squared is a positive. So that whole thing will be positive. So looking at this on my left end of my graph, since it is positive, my curve will be above the slant asymptote. So on the left end of my graph, the curve will be above. So just looking at this all together, again, I'm a little unsure as to what's happening in the middle right now, but I know that I have a slant asymptote and the ends of my graph look like that. Again, I always like to check it on the calculator just to make sure I am correct. So was the right end of the curve below? Let's look. The curve is in blue and it is in fact below. Was the left end of the curve above? So curve is in blue, left end, it is above. So I know I did that correctly. So the key to these questions is definitely the long division and then the limit of the remainder. So if you guys want to do any extra practice for long division, I have some questions here and their corresponding answers here if you just want to practice long division. Always a good thing to practice. Okay, so slant asymptotes, oblique asymptotes, are really like your good friends. You can cross them, but you'll stay close in the end. So textbook questions there for you. Omit part F and just sketch the asymptotes, and that's all you have to do. We're not going to do curve sketching yet. Just talk about the behavior and sketch the behavior of the slant asymptotes. Okay, that's the end of 5.6. Hope that helped.